So good afternoon. Your dessert has been plated, and we welcome you to today's panel on collaborative combat aircraft. I'm Heather Penney, a senior resident fellow at the Mitchell Institute for Aerospace Studies. As we've spoken about today, the United States faces a complex array of global threats. China and Russia are rapidly advancing their military capabilities and challenging U.S. leadership and interests. Russia threatens Europe through its war to seize Ukrainian territory and undermine its sovereignty. At the same time, global actors like North Korea now is rattling its sabers and demonstrating its advancing missile development and sending troops to Ukraine in support of Russia. Iran is launching salvos of rockets and drones into Israel while also supporting Russia. And this evolving landscape demands innovative solutions from our armed forces so that we can shape these global dynamics, deter aggression, and prevail, win if needed. Meeting these challenges will require capabilities that only the Air Force can provide, and we heard that earlier today from General Alvin. Ensuring that our airmen can secure air superiority, penetrate advanced threats to project power across vast distances, and operate in highly contested environments will be crucial to success in any peer conflict and across all of the mission areas. None of this will be an easy job. The Collaborative Combat Aircraft Program represents a key opportunity to address these challenges. CCA, operating alongside and in coordination with manned aircraft, have the potential to expand our combat capabilities and capacity. CCA can potentially act as force multipliers, enhancing the effectiveness of our crewed aircraft through extended sensor and weapon ranges, electronic warfare support, and by complicating enemy targeting. In addition, they can also change the risk calculus of an operation by detonating, disrupting, depleting, degrading, and desynchronizing adversary forces. To discuss the promise of CCA, we're fortunate to be joined by four incredible Air Force industry leaders. So first, Colonel Tim Helfrich, Senior Materiel Leader in the Program Executive Office of Fighters and Advanced Aircraft for the Air Force Lifecycle Management Center, Air Force Materiel Command. Next to him, we are glad to be joined by Mr. Mike Shortsleeve, Vice President of DoD Strategic Development at General Atomics Aeronautical Systems. We're also pleased to welcome Mr. Robert Otis Winkler from Kratos Defense, where he is Vice President for National Security Programs. And next to him, we are thrilled to be joined by Salmon, Vice President of Air Dominance and Strike at Anduril. And finally, last but not least, we're happy to have Mike Benitez, Senior Director of Strategic Product Development, Shield AI. We've got a lot to cover in this short time, so thank you everyone for joining us. So what's interesting about this panel is that rather than having a futures representative to discuss CCA, we have someone from the Air Force Lifecycle Management Center, because folks, it's getting real. A lot of focus was placed this past September at the ASC conference on the missile truck concept of Increment 1 CCA, which, as you know, was awarded General Atomics and Anduril. Folks, can you please update us on the progress of Increment 1 and share any lessons learned during the course of its development?
Okay, I guess I'll get started.
We got to kick it off somewhere.
So I guess one of the great pieces of information is we just finished up basically critical design review for both Anduril and General Atomics. Both industry teammates are on the path to get to first flight in a timeline that allows us to get operational capability by the end of the decade. We are on track, if not ahead in some areas. And I guess one of the biggest lessons that we've learned so far is that we need to be able to know when enough is good enough. If we are to continue to add capability and gold plate things, we're going to miss out on our cost and, most importantly, our schedule targets. And so making some of those tough trades to say this is good enough and moving on has been a challenge because we won a lot, but we are making those decisions.
Mike, Zim, I'd love to hear your perspectives.
Yeah, so I think you said it well in the sense that, hey, we're already moving. We're moving out, right? We're starting to build. We're going to be ready to do our first test flight soon, we'll say. But what I would say from a lessons learned standpoint is, people sometimes think that building an aircraft can be easy. It's not. It's different in most cases for each different airframe that you build. So we've had to actually leverage our 30 years experience doing this with 26 variants that we've done, and we've done a jet UAS before the XQ-67. But I think what gave us a leg up in understanding how this needs to move forward is when we did the XQ-67A, that effort to build that X-plane, with about, I'll say 70, 80% carryover into what would be CCA. That helped us to understand, not only how that design needs to work, but also how do you actually build it, right? That becomes a big factor in manufacturing and production. And if you want to go fast, you've got to understand that. So having that as a background for us as a lesson learned, we picked up a lot of things from that just to understand where we need to go forward. But I will say the challenge also is that you're going to have to add the autonomy aspect to that too. So that's going to be a huge challenge that's still going to have a lot of lessons learned going forward for everybody. But we're moving on. We're ready to go. We're able to go as fast as the Air Force wants us to go.
Yeah, it's actually incredible to say, like, we're on schedule right now, which is not something we hear too often, but that's something that we've been really focused on for the past, let's say, 6 months to over a year. And I think, and I agree with everything that's been said so far, but one of the things that we've really, we've learned through the process is if schedule is king, and let's be honest, this is a very aggressive schedule, being able to field CCAs before the end of the decade is going to be tough. But if schedule is king, you need to ruthlessly pay attention to schedule. And there's going to be trades that needs to happen, especially when you're doing so much learning. This is the first time that we're building and prototyping an autonomous vehicle this quickly, especially this complex. And so everybody's learning. Industry's learning, the government's learning, and the only way you actually do this is through close collaboration. And so something that we figured out is the value of that collaboration and that trust between the government team and industry is actually one of the big pieces that's enabling schedule. We get to discover very quickly, we get to learn and make decisions very quickly, and the way you do that is you work closely with your government partners, you bring them in. The government team has access to a lot of Anduril's facilities, a lot of Anduril data, and these are things that we're doing together. So that we can stick to schedule, but also cost and performance, right? Like, these are things that just need to happen very rapidly, and you do it as one team.
So I'd like to open this question up to all of you. And Tim, you had mentioned this previously about being able to control our appetite for capabilities in order to be able to meet cost and schedule. So how are you balancing speed, affordability, and capability as you all are looking at how do we deliver on CCA?
Yeah, I'll get us kicked off here. So it's pretty clear, and Zim talked a little bit, schedule is the priority. Speed to ramp is the priority. So there's often this saying of, cost, schedule, performance in acquisitions. Whether or not you subscribe to that or not, we could have that debate later. Love talking about that stuff. But in this case, it is schedule, then it's cost, and as long as you meet the minimum operational capability. And we are driving, we know what that capability is that needs to be successful. And so instead of adding features on, we are making the tough decisions to keep that schedule and to keep the costs low. Because if we're going to build in mass, we have to keep the production costs low.
Yeah, I'll add a little bit to that as well. So it reminds me of sort of the Norm Augustine, one of his laws, where he talks about, by 2054, the entire defense budget will be able to buy one aircraft, right? And the Air Force will be able to use it for 3.5 days, the Navy for 3.5, and the Marines will get it every leap year. We can't get to that point, right? There has to be a cutoff point at some point in time has to happen for that. So when we talk about affordability, I look at it, I'll put my old A8 hat on when I did the C2 ISR panel, and I'll just say that it's life cycle cost as well, right? There's a multitude of things. You can have a procurement cost that is how much the aircraft's going to cost, but how much does it take to operate it? How much does it take to do the maintenance? Is there any training associated? What about the logistics? There's a whole tail of costs that need to be looked at as well. And so the ability to kind of look at it from a whole perspective is really what you need to do with CCA if you want to keep it affordable, right? Affordable can be subjective, to be honest with you. So that balance between affordability and capability, certainly there are ways that you can bring the cost down. Added manufacturing could be a method of that. Different types of tooling, different modularity, open architecture, those type of things can help bring those costs down. But the reality at the end of the day, CCA needs to be able to excel in combat, but be cost manageable, because you cannot afford high exquisite capabilities. Not to say that they're not needed, because they are, but if you're looking to kind of gold plate or have a ton of these things out there, that the price point needs to be in an area that is affordable based on what you need it to do in combat.
Yeah, so I love this idea of controlling for time and speed to ramp. And I think that when you look at it just historically, things that end up driving up costs are the creeping requirements creep, or the inadvertently requiring concurrency and having concurrency sneak into the program. And I think that you guys are doing a fantastic job of managing that. It's $8.8 billion across the FIDEP in order to get this done, right? So it's pretty well resourced right now. But I think that in the end, the first generation of everything are going to have warts. And the acceptance of those warts and making sure that you can actually set a bar that says, we'll accept these level of warts, right? But this is the minimum mission requirement, that min viable product. And then moving forward with Inc. 2 very quickly as well. And then continuing that spiral development is going to get us a warfighting capability before the end of the Davidson window, which is, I think, extremely important to deter China.
Now, Zim, I'm going to ask you specifically, because I know that iteration is part of your plan. So can you speak a little bit to the iteration that Otis was just mentioning?
Yeah, I think a lot of it is just trying to wring out risk as early as possible, right? Not approaching it so much from a traditional linear design and development fashion, but understanding like, okay, so we're going to get some things wrong. We know some things are going to go wrong. How do we understand what those are? And then how do we wring out those risks as much as possible? And this is in the context of Increment 1 design, right? Instead, like, there's a lot of things we're doing for HITLs, for example, and understanding like, okay, this is a critical component, and if this is not going to work, we need to know now rather than 6 months from now when we're trying to put the aircraft together. And I think those are all key features to help us accelerate kind of the prototype of Increment 1. But I think on the broader question of iteration, we need to treat schedule as an actual capability, right? We often been separate. You have capability or performance, and then schedule is a separate item. Being able to deliver capability at a certain point is a capability. Being able to deliver a certain capacity at a certain point is a capability. And so when you actually think about it from that perspective, being able to design all of those things in to hit a certain amount by time frame is critical. And then what you kind of think through afterwards is like, how do I add on top of this, right? So I've achieved my critical capability, which is delivery of capacity in this window. And now I think, how do I add on top of that? And it's both a combination of hardware and software.
So Paco, I don't want to leave you out of the conversation because iteration is something that you also do at Shield AI regarding the development of autonomy. So can you please speak about how your company approaches that, and then also how you feed that into the hardware?
Sure. First thing, I just want to go back real quick. If you have an F-35 and you take the pilot out of the F-35, the F-35 does not suddenly become 80% cheaper, okay? So there are significant design trade-offs and choices being made in this program, and so just hats off to everyone that's involved in that and making those hard choices to stick to the schedule. So with that being said, when there was a conversation earlier from the B2 rep up here on the stage, and he said, hey, one of the things we did earlier this year or last year was we separated the flight software from the mission software. Well, guess what? That's exactly what we are doing up on this stage, and that's our approach to integrating mission autonomy. So replace software with autonomy, because it is software, and you have basically flight autonomy or platform autonomy that's on the platforms that are from the stage, and then you have mission autonomy, which is what Shield AI does. And so we are actually providing more advanced missionized behaviors and tasks to actually complete a mission within, call it your design reference mission. And one of the things that we've been doing, and I'll choose our efforts at Kratos over the past year, we've integrated on the Firejet, and newsflash, Kratos actually has autonomy. I know you wouldn't think that platforms don't have autonomy, but remember what I just said, platform autonomy. The MQ-9, General Atomics, actually has pretty robust platform autonomy. But what we're talking about is putting our mission autonomy and integrate it with their platform autonomy. So we have two different types of autonomy, two different types of language, and we have to integrate those. And so the architecture, the interfaces, and how that actually comes together is a non-trivial problem. And I know we're working on that with our partners in government and industry. And so what we did with Kratos, we integrated our HiveMind AI pilot on the Firejet. We went through their it's called an AVCL, their control laws, and we've integrated all those things together. We've taken those lessons learned, to your point about iteration, And we're now extending that into a Navy program on the BQM 177. That is going to become a derivative that Otis may or may not talk about later called Athena. And that is very, very exciting of how we're advancing mission autonomy in the industry space. So very, very exciting things happening in that.
Maybe, I don't know if I'm allowed to do this, I'm not the moderator, but maybe let's like start going down the thread of autonomy because it is central to collaborative combat aircraft. And Paco talked about this quite a bit, but without using the words, but we are developing a government reference architecture called the Autonomy Government Reference Architecture. Let me just step back a couple years on this. So we did quite a bit of market research and analysis with some of our teammates in industry and ACC and in the A5 and an assessment of how is America really doing at developing autonomy, right? And you can see if you plotted out the capability over time, over the last couple decades, for both automotive and air vehicle, it's eye-watering how well we are doing with autonomy. Extremely capable. The one drawback that we found in almost every case is that autonomy was only for a specific platform, right? So you couldn't separate it from the platform and use it in another one, and it was highly vendor locked, right? Which is not the route we wanted to go. And so we've spent this time building with a consortium of industry, right? So air vehicle providers, mission system providers, autonomy experts to build this architecture. So setting standards and interfaces so that we can separate that flight autonomy or platform autonomy from your mission autonomy. So right now on CCA, we are competing out separately the air vehicle and the autonomy that will bring it together, or that will do it in a tactical mission sense. And then we will bring that together in the Air Force working with our industry teammates. And so it's a power to have continuous competition and allow us to continually upgrade that autonomy without vendor lock and without many of the airworthiness and regression testing burdens that we have typically had.
No, I mean, I would just foot stomp, like the beauty of the architecture is one, you kind of enable the ability to get best of breed, right? So the hardware provider isn't always necessarily the best software provider, vice versa, but then also it enables iteration, right? And so in some instances, the air vehicle doesn't need to change, but you can change software very quickly. And the barrier to entry to software is actually pretty low compared to building a vehicle. And if you have standards or architectures, that it actually opens up the marketplace even more, so you can get more companies to really join the ecosystem, and now they know what they're developing against rather than trying to solve the problem in a vacuum. And so in many ways, it's going to bring in more competition, which is a good or bad thing depending on where you sit. But it does enable you to get better technology a little bit faster, and because you've really disaggregated the two, right, you allow that iteration on software in particular to happen very quickly.
Can I just go back real quick on the autonomy? So purposely didn't mention AGRA, but if you go back to G, the government, there's the quote from Ronald Reagan back in 1986. I'm here from the government, I'm here to help. I will say that if you want open standards, so MOSA, WOSA, choose your acronym, you need two things. You need standards, you need well-defined standards, and you have to have governance, which means you have to have someone to maintain that architecture, evolve it, and iterate it as the conditions change, as industry changes, as the mission use case changes, as the sensors change, as the platforms change. And so one of the things I just want to advocate for, that once this AGRA thing is not a once and done thing, it is an enduring commitment that requires continual funding for industry and government to keep it alive and evolving. And that is going to be one of our unique competitive advantages that we have of bringing autonomy for US-based CCAs.
Yeah, so I'll just add, I think it's a great conversation, but I think I'll add one more thing that's important for open systems or GRA, and that's the government to actually make the integration decision. They don't actually have to put the software into the system, but they should be the one that decides on the sensors, right? They should be the one that decides on the autonomy. And I know that's been the ultimate goal. It sounds like this is finally the program that it's going to happen in. But in previous programs, it's very hard, right? And it's the Air Force, really the DoD in general, has given up this skill set, and we need to build it back in, right? We need to build that back up. So I'm really glad to hear that that's happening now.
So with the autonomy government reference architecture, that clearly allows you to have more competition in terms of the standards and allowing vehicle autonomy as well as mission autonomy. Can you speak more to how you envision developing and evolving the mission autonomy as you get different combinations of sensors and avionics and weapons and so forth? How would you put all of that together, assuming that the vehicle autonomy maintain some more stability than you would have with the mission autonomy?
Yeah, what I'll say is one of the things that you look at autonomy, and it looks a little bit like a video game, right? From what most people can see it, they see a playback, they see a simulation. That looks like something you see in a video game. And to some extent, it is, and that's kind of where the similarities end. So when we think about going from sim to real, or from simulation all the way into live flight, and then going through that process, that is a significant emotional event, and it requires a set of expertise, a depth of technology as a baseline on which to extend. And so when we think about it, we start with for every 1 hour of autonomy flight, that 1 hour, if we back that up, has been through a hill or a HITL, a hardware in the loop, and that is probably like a 10-to-1 ratio. So there's about 10 to 100 hours, we'll call it, actually it's 100. So we do 100 hours of hardware in the loop with real systems in a physics-based environment to validate the sensors, the integrations, and the flight performance characteristics with that platform autonomy. So that's 100 to 1. If we back that up, we have a systems in the loop. This is a high fidelity, real time. That runs at about 10,000 hours, again, to that 1 hour of flight time. And if we back that up to the beginning, we have a low fidelity systems in the loop process that runs faster than real time, and it's 100,000 to 1. So for every 1 hour that you see of mission flight autonomy, that's 100,000 plus 10,000 plus 100 to get to that 1. So that requires a significant amount of expertise. It requires, again, that technology. And so we think about tools, the tool chains, and the pathways to orchestrate that to do things like batch testing, where I could run 10 of these at once for 100,000 hours to get to that time that I need. So there is a lot that goes into it. You get into domain randomizations and test orchestration and design of experiments, and you quickly realize, like, this is not easy. It's really hard. And so that's how we think about doing that. And if you take that process and go, okay, I want to do it with Anduril this week. Next week, I'm going to pivot and I'm going to go with General Atomics. And the week after that, I'm going to go with Kratos. You have to have a tech stack that is able to do that. If you can only do it once and you can't adapt to it, you can't change the payloads, you can't change platforms, you're not going to be valuable for long.
Yeah, I mean, I would really foot stomp the importance of getting to a baseline product that removes as much hardware bespokeness as much as possible. Otherwise, you're developing software for one application and one application only. And so in many ways, you have to, especially for mission autonomy, you can think about it like, what are some core functions that need to exist regardless of what it's on? Is it swimming? Is it flying? It could be anything. And you spend that time developing that. And that's actually the bulk of software, right? And as you get progressively closer to the hardware you're going to integrate on, you add a little bit more specific software, but it cannot be the core of the capability. And so when we're thinking through, like, how do we actually develop this product, right? When we talk about Lattice for mission autonomy, it is going on our UAVs, it's going on our UUVs, and it has to be able to support all of these things. And you have this single product that is able to branch out and have different mission sets, different platform integrations, and support multiple use cases, sensors, capabilities. But because you have that baseline product that is common, you're actually getting the best learning from different applications. You're also combining and getting efficiencies on your team. And to Paco's point, you build out your testing regime to be able to support that. So when we're talking about modeling in sim and doing our runs in a digital environment, that's usually your baseline product. It's not that closely modeled to a specific platform. And you can slowly move up to something that's a little bit more representative. And even when we talk about, Anduril does a lot of surrogate flight tests. We're talking about, a Group 3, like 50-pound fighter jet looking thing. It's not actually going to be a CCA, right? But it's kind of close enough. We're building out test plans to understand like what are the things I can actually test on the surrogate, and then rings out my risk there before I do an actual integration on a platform. So there's a lot of like thoughtfulness that needs to go into how we develop the software so it can support a lot of different applications. But it's something that like I think most software companies have been working on for years.
Let me add to that. So surrogate testing is absolutely critical because it allows you to reduce the risk upfront in your development. So the surrogate testing can be in a simulation environment, or what you really want to do is put that algorithm in an imperfect conditions, which is your real world flying, right? Put it on an aircraft to get out there, kind of what she was talking about, right? We've been using our MQ-20 in that realm. And what we're finding is that you can do all your reps and sets, in what's sort of referred to as offline type of learning, where you can do large scale computing, you can have that thing do thousands and thousands of times. That's kind of what Paco was getting at, right? So you can kind of help perfect it. But then once you put it into the real environment, now that you're going to get conditions that perhaps you didn't think of in the simulated environment. And so the value starts to go up at that point, right? It also helps you with understanding what kind of processing power is going to be needed to do this, because we're talking huge amounts of high-powered computing that needs to be done. Now, the good thing is that things are getting faster, cheaper, and doing things much better than what they have in the past. But what we've found with the surrogate testing more than anything is it's validated the fact that you want to have that separation of the vehicle autonomy and the mission autonomy. And so we've been able to do this testing on our own research and development efforts to where we've been able to upload over the air new algorithm and skill sets, and allowing the aircraft, in many cases, to do its own reinforced learning for a problem set that perhaps it didn't quite understand. So it's able to do things sort of on the fly. The reason for that is we've separated that vehicle autonomy, so we know the flight critical safety aspects aren't going to get affected. And we've done this numerous times. And oh, by the way, the FAA has approved us to do this. We've got 2 airfields in the deserts of California, but we're flying in public airspace. So the ability to show that there is a safety factor built into that allows you to go from the simulation environment to the real world, which is really what's going to give you the validation I think that's needed for CCA and autonomy.
Yeah, and one of the great things that we're also working in conjunction with Collaborative Combat Aircraft with the overall program is an effort we're doing with DARPA called Venom. And so what we're doing there, if you're not aware, is modifying a handful of F-16s at Eglin Air Force Base to make them into autonomous vehicles, and so that they will be compliant with the autonomous government reference architecture and essentially be test beds for an enduring amount of time, so that not every company that develops autonomy has aircraft to go use as test beds. And so we want to make sure that we can maximize competition, bring best of breed, and make in-flight with a pilot on the loop, be able to pickle off the autonomy if it's an issue, but have test assets for them to be able to use and bring their cutting-edge autonomy to bear. And so we'll be using that in the coming year, working with our teammates in DARPA.
So I want to go back to the processing piece, right? With autonomy and processing power. I mean, Mike, you'd mentioned, and you yourself, Paco, had said, hey, look, this is going to take a lot of software, a lot of processing in order to be able to learn and teach the agents. But we clearly don't have a tremendous amount of SWaP-C on the vehicle. So can you describe how you are compressing the software size so that it can exist on the vehicle and doesn't have to be tethered all the way back to a data center? It's just simply tethered amongst its swarm or to its human teammate.
Yeah, that's a really great question. I'll start and I'll hand it over to Mike, because I think you have some of the different architecture that you just described. So when we think about, let's back it up real quick. Let's talk about AI versus autonomy. So the AI is the tool, the autonomy is the product, the outcome, right? So we use the AI tools and tool chains to build autonomous behaviors. Those autonomous solutions, I think most of industry is settled on a hybrid architectures, which are a combination of heuristics, expert systems, and reinforcement learning. Those don't actually require a lot of data to start training. When you get into the ground-based regression testing, there's a lot of synthetic data and stuff that goes into it. But once you actually deploy it, those parts of the autonomy don't require too much. You can get away with a couple CPUs. But that is going to support your cognition and action. As you add sensors to the CCA, your perception stack on the autonomy is where all of your GPU requirements come from. So computer vision, sensor fusion, things like that, those require processing that the SWaP-C formats currently do not support to the level of, again, if you think of an F-35, if you took a pilot out and put a compute cluster where the pilot was, that's kind of how it looks right now. Obviously, not exactly, but as you go back to the CCA program, without getting into the specifics of how it's configured, there's definitely deliberate design choices, not only based on cost but complexity. And the perception side of the autonomy stack introduces a level of complexity that is definitely going to be needed down the road, not just for CCAs, but a whole bunch of other things that are coming. But for this particular project, I think it was deliberate choice to constrain the perception side of the autonomy stack.
You, Mike. It's important to understand that when we talk about autonomy within a CCA context, the autonomy really, we maybe should be saying the word independent, because it's not being human directed per se. There's human teaming that's going on, but when we say autonomy, I think in our social circles, that's a colloquialism for AI ML, which is a completely different mathematical paradigm. And so I just want to provide that clarification. As we're up here on stage talking about autonomy, we're really describing the independent capabilities of the CCA and its software stack, not necessarily the AI ML.
Yeah, so to add a little bit and to concur completely about the sensor side of the house, that's when you're getting all the raw information, right? That's when it needs to, let's say you're using a auto target recognition type of capability, right? It needs to be able to detect not only what's out there, get through the clutter, but then identify specifically what that target is, so that processing is huge. But so the output of that is what goes into sort of the decision making, which doesn't require as much. To kind of put it in perspective, because we've done with our own research and development, and then we're also on contract to do the smart sensor work with CDAO, what we have found is you start talking about on the sensor processing side, it's like 20 to 25 teraflops. And what is that? Well, a single teraflop is like 1 trillion calculations in a second, right? That's huge, right? That needs to occur just on the sensor side to be able to get through the clutter, find out what it is, and all of that. So when you look at that, you go, wow, that's pretty significant to be able to do the actions just to get the sensing capability that's going to feed the decision maker on it. So that becomes a lot of computing processing power. But I said earlier how things are getting, faster, smaller, and cheaper in some ways. I mean, to put it in a sort of an analogy for you, if you were looking at, if you own a PlayStation 5 or the new Xbox, that already has like 10 to 12 teraflops built into it, right? But if you're from my age of 70s and 80s growing up with the Atari 2600, it's like 5 billion of those that you need to do that. So it's changed. Things have gotten better, smaller, cheaper to be able to do the things. But for us, the big aspect of this is on that sensing side. That's where the bulk of that processing is going to take place. So what we have done from a surrogate testing perspective with this is we've looked at, is it, you put the processing on one aircraft and it feeds the others, right? We've done this in a live virtual construct as well. So we're trying to figure out different ways to make that happen. The other ways are you do that sort of, offline learning with large-scale computing, and you get the reps and sets down to where you can get it small enough that it can go on something that doesn't require, a gazillion type of teraflops. So there's a lot of work that still needs to be done with this, but the processing, while the outlook looks good, it's still challenging today.
One go back real quick, or I guess pile on, depending on how you interpret it. So a question might be out there is like, well, if I don't have any sensors and I'm not perceiving anything, like what good is the autonomy? Which is pretty good question to ask. I'm glad you asked. So if you look at, I'll use an example. So DARPA ACE. We flew on DARPA ACE. It just concluded. That was awesome. We did 4 years of flying and about 60 dogfights, which is awesome. But it had no perception. It had no sensors. So DARPA ACE had no sensors. How did the autonomy that's flying on the Vista actually know how to maneuver in relationship to the Bandit? It did that because it flew with a slate pod on the wing, if you look at the pictures, and it's actually getting fed data link information of its surroundings, and it's using that to feed the cognition core to then make its actions. And so there is a huge opportunity when we talk about data links. The data is so important. If you can make sense of that on something like a wedge tail or an F-35 or an F-22, and you can push that perception of the environment to the cognition core, that is the real power of how you break the cost curve of these platforms. Otherwise, you're just going to have an unmanned F-35.
Yeah, I'll just add, I think that to capture that, right, I look at it as a scale between the amount of connectivity that you have versus the amount of autonomy that you have. And if you have to have a full-up autonomy, self-perceiving everything, you're stuck with a very, very expensive system. And then,
Don't get me wrong, F-35 is awesome, just to be clear.
but for a CCA at least. But backing that up, then those are the trades that you make, and I think that that's what's going on right now. But I think we get lost in this idea of what we forget about the levels of autonomy when we're trying to describe this stuff.
So Colonel Helfrich, we're clearly in the process of Increment 1. How do you envision moving forward with Increment 2?
Yeah, so great. I'm glad we get to talk about Increment 2 because actually one of the ways that we've been able to control or put appetite suppressant on adding things into Increment 1 is that our original plan was, and the funding that was laid in was for 2 increments. And so, you can, you don't have to get everything into this Increment 1. What we need to do is get it out there with the minimum viable capability on time or early and on budget or under budget. But Increment 2, we are like danger close to getting started in earnest on that. Frankly, we're doing government analysis right now with FFRDCs and internal government agencies to kind of look to make sure we understand what are the right mission use cases for an Increment 2 and the top level attributes. And then next year, actually this fiscal year, we will kick off concept refinement where we then bring in industry to help us further refine what those attributes are and whittle down those use cases. It's really the same approach that we did for CCA Increment 1, but now CCA Increment 1 is a new player in the environment as we do the analysis. And so that's where we're going, and you'll see us begin concept refinement later this year.
So Increment 1 is really envisioned as being a little bit of a missile truck, right? Doing a human-machine teaming. And we heard some of the senior leaders talk about the relationship and how they have tested the ability of combat pilots to be able to control and interact with these vehicles in the battle space through simulation. So to get to the human-machine teaming element of that, how do you build warfighter trust?
Well, I'll get started, and I think a lot of teammates up here who can help me out. But I talked earlier about Venom, which is like a parallel effort along with CCAs. Another effort the Air Force is doing in parallel is the Experimental Operations Unit. And it's kind of a fundamental way to think about it. We are very good in the Air Force of building the next thing to replace the last thing we had, right? F-15, F-22, F-16, F-35. But the CCA is coming in, and it's not replacing anything. Some people say, oh, you're replacing UAVs. No, you're not. This is a fundamentally different mission set, and it will be operating in a fundamentally different way. And so the Air Force has stood up a unit, the Experimental Operations Unit, which are focused on getting the force ready to integrate CCA when CCA are ready. And so we work hand in hand with them every day to make sure that we're providing them the right capability, the right resources, so that they can go out and do the testing and do the experimentation. And kind of the fundamental way that they're going to do that is a build-up approach, as you might expect. First thing we want to do is we want to get pilots, operators into the simulator cockpits. Think JSE, VWC, Virtual Test and Training Center. Get them in there with simulated CCA models in those environments, and so they can get a chance to fly with them in the virtual environment. Next step after that is then we're able to fly live flight with our platforms, our FIT-10 platforms, and simulate the CCA into that platform, the next set of trust. And then after that, we will do experimentation with both live fly of our FIT-10 platforms and CCA, kind of building that trust over time.
So what kind of feedback are you receiving from your pilots and operators?
I guess initial feedback that we've seen is, and this is probably, should be self-evident, right? But the more autonomous the platform is, the less workload it is for the pilot, and therefore how many CCA can they take custody of at one time. But we have found some combinations, even early through anecdotal evidence, that pilots will be able to take custody of more CCA than we had maybe originally thought. And as we build out better and better autonomy, those numbers can just go up.
So Otis, I know that you just recently flew a Valkyrie with the Marine F-35s. How did that go?
Yeah, it went fantastic, actually. It was the first time that any DoD person had flown a CCA-type aircraft in a missionized configuration. And it was really nice. It was flown with a 4-ship of F-35s and then a 2-ship of Strike Eagle or EXs as well, and an Emerald flag with a missionized package on the Valkyrie to demonstrate disrupting an enemy kill chain. And what we found was that the disaggregation of sensors was unbelievably powerful. It actually completed the overall mission set in a way that was additive to what we would get out of a traditional man fighter, right? So it really proved out the thesis. And what we also proved out is it is unbelievably important, and you just talked about it, it's unbelievably important to get these things in the hands of the warfighter. The way you build trust is you get it in the hands of the warfighter, and that's what we learned coming out of that test or that demonstration. Putting it in the hands of the warfighter will allow them to build trust, right? And it gives them the ability to shape the mission sets and to shape the mission package that are going in. Now, the Marine Corps doesn't have the $8.8 billion, right, in order to do this across the FIDEP, so they are really focused on a min-viable product for a very specific mission set inside the first island chain. And so I think it is still, the Marine Corps and the Navy are still part of the overall CCA program, so there'll be a lot of lessons that come back and forth with a min-viable product on autonomy, right, because they are taking a much more simple, quick focus on autonomy, right, and then they'll grow into the autonomy overall. So it's a great opportunity.
I think the only thing I would really add to that, because I think getting it out and flying and getting warfighter hands on it is kind of an obvious answer of how you build trust. The only thing I would add to that is how we think about the development of the actual software itself. I think there's a lot of great technology out there when we talk about autonomy, but really kind of where we are and being able to support quick fielding and that building of trust, you usually want to start with something a little bit more deterministic, right? So you understand what it's supposed to do, and if it actually does that over and over again, that's how you actually build trust. And so kind of that understanding of how do I work with the machine, you actually need to plan into how you're going to architect your actual autonomy and how you want it to be operated, at least for the initial touch points. And as the services get more comfortable with having autonomous robots in their environment, you can do something a little bit more technically advanced, but I would say if the goal is to get it out there as quickly as possible, generally something deterministic gets the job done is an easier approach.
If I could add to that, so when you're talking about building that trust, you got to look at the existing processes that are already in place, right? You got developmental testing, you got operational testing, right? So the operational testing aspect sometimes can be pretty lengthy to get to what you need to deliver. But I think getting to the point, like what Otis was saying, if you're getting it in the hands earlier and you're able to do this in an iterative process as you are doing the development, you probably could reduce that timeline for not just development testing, but the operational testing as well. But I will say that that's going to be a challenge is, for trust, it's not just about them getting the experience and the reps and sets and things like that with these platforms. It's about it going through the full process of testing to validate that it's going to do exactly what it needs to do. So that can be a lengthy process. When you look at programs that exist out there today, you usually develop the whole platform and then you take it into the actual testing. You need to look at some ways to maybe reduce that timeline by doing some iterative type of things as you can.
Man, I love that. I think we got the best test organizations in the planet in the United States Air Force, but there are ways to do it faster. I think we've seen combined DT and OT opportunities, and going through this with the idea that, hey, you heard it earlier today, we should treat ourselves as a bit of an underdog as it comes to this getting things to the field ASAP to at least deter, if not to win against China. And so by doing things in a different way, right, speed things up, we can really make some money.
Are
Yeah,
you
just-
seeing,
just on-
go ahead,
just
Paco.
real quick. So this is, this day has the word futures in it, so I just want to talk about the future for just a second. Even not the far future, the near future. So all of the things that we just said is going to work now. But I'll tell you, China is not going, our test infrastructure is really hard. This is going to take the payloads off of the CCA, and we're going to take the autonomy. We're going to use the simplest things possible, and we're just going to throw it out there. That's not what they're doing. So just realize, we have to maneuver in relationship to our adversary as well. And so rate matching what they're going to do. They're unencumbered by some of the same bureaucratic processes that we have. Our processes, I lived in DT and OT, love it. It has a time and a place. We have to accept some risk along the way. So when we look at what do we actually need to do in the near future, what's next? We look at, say, Increment 2 or some other stuff. We need to be thinking more thoughtfully about autonomy. Autonomy is not this monolithic thing. There's all kinds of types of autonomy, mission autonomy, in fact. What we're talking about here is very low-level autonomy. Call it level 2, level 3 maybe. When we get to level 3, level 4, you're talking about cognitive autonomy, reinforcement learning. You're actually using AI to inform your autonomy algorithms. And that is going to require, based on trust, we have to evolve how we think about building that. And so RLHF is one of the processes we use. It's reinforcement learning via human factors. So we actually have people embedded. We have currently flying F-22 pilots, F-35 pilots, B-2 pilots, MQ-9 operators in our engineering labs, going through our algorithms and seeing how they're built and actually establishing trust in the sausage-making process. So we have pioneered a few different approaches, but we're trying to think about the future. Advanced autonomy is going to be where it's at. And the reason why I kind of was a little wishy-washy, we've talked about this for probably a year now, the Air Force has still not defined autonomy. And so it is a recurring blind spot that we have. So hats off to the Mitchell Institute. Actually, Heather, you wrote or co-authored Beyond the Pixie Dust about 2 years ago now, 2.5 years ago?
Yeah.
Basically calling out the Air Force for this gap. This 2.5 years later, still no definition of autonomy. So we're working on it. Industry's going to keep pushing hard, but we're going to need that thought leadership from the service to help us get us across the finish line.
Thanks for that shout out. Pixie Dust is probably outside, so pick up a copy on your way out. This has clearly been a very robust discussion. I do want to open up the conversation for questions from the audience. In the back?
Thank you. Hey, Jeff Patton from Elbit America. Earlier today we heard about the importance of designing for exportability. And that's something we haven't talked about in this panel. Can you talk about how CCAs and AI is being designed for exportability?
Can I go first, and I'll hand to you?
Sure.
I have a unique, I am platform agnostic, all right? So I have a different view of the world that I think than other people on the stage. So I will tell you, there is a massive demand signal on the international market for CCAs. I'll also tell you, there's at least 7 different international programs that are all funded building different types of CCAs or doing concept development for that. So I think there's a real opportunity from the platform side. You look at exporting platforms, you look at licensed production, co-production. There's all kinds of really, really great industrial tools that we could use to proliferate the CCAs. But at the end of the day, it's also going to come down to the software. And if we think that governance of our software stack and that AGRA is going to be our unique, compelling advantage, I defer to the Air Force for discussing that.
So I love that question. And I will say that the biggest impediment that we have it's not making it exportable, because they are pretty much, everybody's going to be exportable. But what's going to prohibit it is a policy. And that policy is MTCR. And that thing has outlived its usefulness, right? We changed it.
I'm surprised. Well, Mike, I'm surprised you're not clapping from MQ9s.
I'm waiting for my turn to say something here on that. But
It's like
It
I
is
planted
nuts.
that
We are,
question.
I'll tell you what, we are seeding our industrial base and our space to influence our allies and partners or to help our allies and partners because of MTCR, right? The other people don't ascribe to it, but we certainly do. It was originally designed to stop the proliferation of missiles, right? These are airplanes, they're not missiles, but they're somehow lumped into that. We should work hard in this administration to remove MTCR from the lexicon and reset it with something else or just move forward, but it needs to go away.
Mike,
Amen.
notice you guys are smarter than me on this. Isn't that voluntary? It's not even like
Well, yeah, so the
It's
MTCR
voluntary.
is not regulatory. It is, it's one of those things where the U.S. has
It's a
signed up and
political
said, hey,
regime.
we'll take the higher ground type of thing, and we'll do this. But there's no restrictions on anybody or anything. Nobody follows up if you're breaking it, so to speak. But what's that? Except the
us.
U.S.
Yeah,
Except the
clearly
U.S.
us.
But I will say, like, just for us with an MQ-9, right, that has been out for years, right, 20 some odd years, we have such huge challenges trying to get that from an FMS or even a direct commercial sale perspective because of that. So to your point, exportability, I think everything that's being built can be, ported over in that frame. And to be honest with you, I think everybody up here is already looking at that, but it's going to be the policy and the restrictions that the U.S. has self-imposed, I'll say, that is really going to limit us in being able to do this with some of our allies and partners.
And I'll say that there was some lightening of the MTCR restrictions, but they are well behind technology. And so if you happen to be a UAS that is very slow, right, and very small and very short range, then sure, then they've lessened those requirements and allow you. But that's not where the threat is. That's not where technology is, and that's certainly not where the United States of America is right now.
Yeah, and the technology is proliferated and it's globally accessible, so it's no longer a relevant regime for us anymore. Next question. By the way, thank you for asking about the international piece, because that was a question on my script that I had passed up, so it's like I had planted it. Sir?
Yeah, good afternoon. John Turpak, Air and Space Forces Magazine. This is for the Colonel, but maybe everybody could comment on it. Help us understand the sequence of the iterations. How long are you expecting CCAs to last? Are you measuring that in terms of months, engine cycles, flying hours? And is the idea with increment 1 that it will proceed to increment 2 and then in a 3 and a 4, or will you go back to increment 1 and maybe have an increment 1B? What are the upgrades, and are they at these various increments, or are the increments themselves the next steps?
So it's a great question, and just know that the Air Force has a lot of learning to do over the coming years. But I do expect that there will be a time where we have a mixture of increment 1s and increment 2s and maybe increment 3s out there, and they will, the mix of them will change based on what is necessary to meet our force design and our global commitments. I do want to just hit on a couple key things there. One is no one should think that increment 2 means increment 1 plus, right? I know that it's 1, 2 is 1 more than 1, but that doesn't mean that increment 2 is more capability. We're still looking to figure out whether the right balance, and we're doing analysis, is to further bring down the capability to maximize a low cost, or is it that I need to maybe change even what the focus is from a missile truck to something else, maybe the electromagnetic spectrum, whatnot. I think it's a little too early to say whether or not we're going to do increment 1B or 1C. We'll have to learn as increment 1 rolls out and as increment 2 rolls out, but we do expect them to be complementary and have multiple increments in the force at the same time. And the life expectancy? Well, so life expectancy, a lot of that has to do with how you build your airframe, right? And so that you do end up with life expectancy just because of, and that comes down to flight hours is how that's typically measured. But again, that comes back to structural load and how much you build it to. And if you shorten the life expectancy, right, then you can potentially take out some weight, saving cost or allowing you to bring other things into the airframe.
Go ahead, then.
All right. We've come to the end of our time, though I will say that from the Mitchell Institute, we do envision CCA having a potential to have heterogeneous missions and that can then provide tremendous value to the force commander as they look to alter risk equations, increase survivability, and enhance human-machine teaming in order to achieve mission effectiveness. So this will be an in-place break. Please do not leave the room. 5 minutes, so at 2:30 we'll start our next panel. Thank you so much.